Welcome to Applied Linear Algebra Lecture 5. Today is special for you guys on YouTube because I failed to record the first time around, so I'm doing a rerun of this one. Two topics for today. They're going to be sort of tangentially related, but largely just separate parts of the talk. First up is going to be symmetry. So if we have a system with some sort of nice symmetry to it, like maybe we can shift it from side to side without changing the system, how can we use that information to more efficiently do things like find eigenvalues or invert a matrix? Then second main topic is going to be how to represent rotations. That one will be sort of a little bit at the end. We'll spend most of the time talking about symmetry. So let's start with an example. Sometimes I have something like a PDE. Let's say del squared phi equals some source term epsilon. So this would be a typical sort of thing you'd run into. For instance, a heat equation would look like this. If you have like some sources of heat and you're trying to find the equilibrium temperature distribution, or if you have some electric and magnetic charge densities and you're trying to find the equilibrium electric and magnetic fields, this is the sort of equation you'd have to solve in order to do that. Now, the main interesting thing here is that there's a symmetry to it. The key matrix that we're going to want to work with is this del squared thing. And this del squared thing is invariant if you shift the whole system left or right or up or down a bit. So for instance, in a one-dimensional system, the discretized matrix corresponding to that del squared guy would look like this. On the diagonal, it's all minus 2's. Then one below the diagonal, it's all plus 1's. One above the diagonal, it's all plus 1's. And then there's a 1 in each corner corresponding to the interaction with the other end of the system. So there's wraparound boundary conditions. Conceptually, what this corresponds to is you've got a temperature or an electric potential or a magnetic potential or whatever at each point along this line. And this is telling us basically the second derivative. We're taking an approximation of the second derivative by looking at a point and its two neighbors. And then at the ends, we have wraparound boundaries. So you'd be looking at this guy, and that guy, for instance. Yeah. So now we want to solve this sort of equation or look at its eigenvalues in order to figure out stability or whatever. How can we do that efficiently? Key thing to notice is that the system is invariant if we shift left or right a little bit. So what that will do to this matrix is basically take this first column, move it to the bottom, first row, move it to the bottom, first column, move it to the end. And if we apply both of those two transformations, then we find that we get the same matrix back. So the way we can write this is that there's this permutation matrix P. P does this thing where it sort of shifts everything right one and or down one. And then, for instance, if I multiply on this side, this will, I guess as written, it will move everything up one and then put the top thing down at the bottom. Or if I apply on this side, it will move everything left one, and then put the last column at the back. So we have this permutation matrix P. We applied it before and after, so it hits both the rows and the columns. And that corresponds to shifting our whole system left to right by one, and it leaves the matrix invariant. So this original equation, where we have del squared phi equals epsilon, would be the same as, equivalent to P times our matrix representing the discretization of del squared times P transpose times phi, or equivalently, it would be del squared of phi shifted by P transpose is equal to epsilon shifted by P transpose. So the key idea here is the operator itself is invariant under this shift operation. So if we're shifting both phi and epsilon, both our sources and our field, left or right by a unit, then the whole equation is going to stay the same. So that's the sort of symmetry that we want to exploit here. And there's lots of other symmetry, like this one comes up all the time in PDEs. But there's other kinds of things like this. For instance, maybe I'm looking at a covariance matrix, and I find that two of my variables are exchangeable. So I have my big covariance matrix, and I can apply a permutation matrix that looks like mostly identities, but then somewhere in the middle I'm going to swap two of the variables, and then do the same thing on the other side. Same thing over here. And if I find that my covariance matrix is invariant under this operation, indicating that these two variables are exchangeable, they're sort of the same, my system is the same system when I swap these two variables around, then that would be another example where like I'm applying the same permutation before and the transpose permutation after, and the matrix remains invariant. We could also extend something like the original example to higher dimensions. So in higher dimensions, instead of just this like three diagonals sort of thing, you would instead have three block diagonals of this matrix, and that would correspond to basically doing the same thing as this, but also in another dimension. And then you could have permutations where you shift up or down or left or right, and that would be like a whole more complicated set of permutations under which the system would be invariant. Anyway, that's the conceptual idea here. These are the sort of symmetries that we're going to start out talking about. What can we do with this? So if we know that a matrix has this sort of symmetry to it, what can we do? So the key thing here is we call our matrix A. We apply P transpose. We have to get back A. Alternative way of writing it, I can move this P over to the other side, and then I get PA equals AP. In other words, the permutation commutes with the matrix. And this is the key term you'd search for if you were looking for information about this sort of thing online, is commutative matrices, or the main thing we'll be talking about is simultaneous diagonalization of commuting matrices. The key theorem here is that when two matrices commute, they can be simultaneously diagonalized. What does that mean? So we think about an eigendecomposition of both P and A. So we've got P is equal to some U lambda P, I guess UP lambda P, UP transpose. It's the eigendecomposition of U. Then A is going to be some potentially different UA lambda A, UA transpose. Now, suppose for a moment that both of these have the same U. So UA and UP are the same. So in other words, they have the same eigenvectors. So this is just U. In this case, these two matrices will definitely commute, and it's pretty easy to see that, because if I multiply them together, then I get PA equals U lambda P U transpose times U lambda A U transpose. This U transpose U cancels. Lambda A and lambda P are both diagonal matrices, and diagonal matrices always commute, right? Because you're just multiplying the things on diagonals. That's just plain old scalar multiplication. Scalar multiplication from elementary school, we know that commutes. So lambda P times lambda A is equal to lambda P, A times lambda P. So I can swap around the order of those two. Get U lambda A P U transpose, and then I could put this U transpose U back in, right? Because that's just an identity. I can do that for free. Get U lambda A U transpose times U lambda P U transpose, which is AP. So we found that PA is equal to AP when these two have the same eigenvector. So like intuitively, what's going on here is when we have the same eigenvectors, we just sort of look at the whole thing in the eigenbasis, and then both of these guys are diagonal, so they both trivially commute. Now, the interesting theorem, which I'm not going to prove, but will state, is that this is the only way that two matrices can commute. Whenever two matrices can commute, they always must have the same eigenbasis. There is a big catch there, though. So the catch is, remember from last time, if we have repeated eigenvalues, so for instance, maybe two of the eigenvalues of A are both 1, then the eigenvectors are underdetermined. So what the key theorem here says is that if these two matrices commute, then there must exist an eigenbasis which works for both of them. So there must be some set of eigenvectors for A, which is also a set of eigenvectors for P. That doesn't mean that every possible set of eigenvectors for A is a set of eigenvectors for P. So trivial example of this, we could take P to be the identity matrix. The identity matrix, all of the eigenvalues are 1. They're all repeated, which means we can pick any eigenbasis we want. Any set of orthonormal vectors can be our eigenbasis. And then, so we can just pick anything, right? And clearly, most of those will not be eigenvectors for A. However, whatever the eigenvectors for A are, there will also be eigenvectors for the identity matrix. So, like, the thing does work. So this is going to be useful. It's going to be most useful in cases where we have the most different eigenvalues. So if you have lots of different eigenvalues for P, you're going to be able to get lots of information about the eigenvectors of A. On the other hand, if you just take P to be the identity matrix, then you get no information at all about the eigenvectors of A. It could be anything, which, I mean, makes sense because, you know, identity matrix commutes with everything, so hopefully that won't tell us anything about the eigenvectors of A. Let's go back to our example. So in our example, we had this matrix with like the 3 diagonals, -2 on the main diagonal, dot, and then 1s below that, above that, 2 corners. And then our P matrix was this thing that sort of shifts everything down by 1, and then shifts everything up by 1, and then moves the top row down to the bottom. So the question is, what are the eigenvectors and eigenvalues of this permutation? Or more generally, given a permutation, how do you find its eigenvectors and eigenvalues? If we can find the eigenvectors and eigenvalues of this, then it's going to tell us a bunch about the eigenvectors of this guy. All right, so let's recurse on that question. In general, how do we find eigenvectors and eigenvalues of permutation matrices? If we could just do that once for all permutation matrices, or at least for some permutation matrices, then we've just gained a bunch of information about eigenvectors of any matrix which is invariant under that permutation. So key trick here is if I look at this permutation, we'll assume this system is size n. In this case, I think I've written this as n equals 5. If I raise p to the n, then I get back the identity matrix. So in other words, because I've got wraparound boundary conditions, if I shift this thing left or right, if I shift this thing left n times, so in this case, if I do 5 left shifts one after another, it'll just get back to where it started, meaning it's an identity. Also, in general, if the eigendecomposition P is U lambda U transpose, then the eigendecomposition P to the n is going to be U lambda to the n U transpose. That has to be the identity matrix, which means these eigenvalues, if I raise them to the n, all have to be 1. In other words, my eigenvalues are roots of unity, nth roots of unity. So we know that the eigenvalues of this guy are going to be nth roots of unity. So things like 1 minus 1, I minus I, in the case of n equals 4, in the case of n equals 5, it would be something like e to the 2i pi over 5, I guess. Or e to the 2i pi times 2/5, so on and so forth. What about the eigenvectors? This one would take a little more calculation, but if you've ever seen something like this before, you may know off the top of your head, or you may guess just from the fact that the eigenvalues are roots of unity. It's going to be Fourier components. So if I apply a Fourier transform to this guy, that's going to diagonalize it. Now, 2 important things come out of this. First, for this particular permutation matrix, or generally permutation matrices in this family, where we're doing like a sort of shift operation in one dimension, and there's like we're doing one step, you do it n times, you get back to the beginning. This is going to have n distinct eigenvalues, the n distinct nth roots of unity. So they're all distinct. That's great. That means whatever our eigenvectors for this guy are, those are going to be the unique eigenvectors of this other matrix. So that's very helpful. This will not generalize to higher dimensions, by the way. If we do like the two-dimensional version of the del squared operator, there will be some repeat eigenvalues, and then like you're only getting partial information about the eigenvectors, but we can handle that later. Anyway, yeah, so we've got distinct eigenvectors, and we said the Fourier transform on n elements gives us those eigenvectors, which means the Fourier transform also diagonalizes this guy. And if you've taken a class on like PDEs at some point, you may already know that. The del squared operator, like del squared phi equals epsilon. Common way to solve this sort of thing is you take a Fourier transform on both sides, right? So Fourier transform hits del squared phi, and that gives you a Fourier transform epsilon. And, you know, Fourier transform operating on a del squared operator turns it into a nice diagonal thing. It's going to be like an omega squared times I squared or something like that. Anyway, this is like the equivalent of a diagonal matrix. It's the important thing. So, if I want to solve equations involving this matrix, what I can do is just Fourier transform both sides, then do a diagonal operation with whatever the eigenvalues of this guy are, and then do a Fourier transform back. Relatively efficient. That topics. So in general, because permutation matrices, their eigenvectors are going to be some version of Fourier transforms. It's not necessarily going to be just one Fourier transform. It may be constructed out of Fourier transforms. So let's quickly cover an example of that. For instance, earlier I had the example where you have some covariance matrix, and then we're saying that two of the variables are exchangeable. So if you flip them around, this covariance matrix should remain the same. And then you have a permutation that looks like this. In this case, most of the matrix is an identity matrix, and it is indeed going to behave like an identity matrix. The only part that's not an identity matrix is this guy in the middle. That swaps the two. And the relevant Fourier transform here is just going to be a Fourier transform on two elements. So this middle bit is going to be diagonalized by a Fourier transform on two elements. Its eigenvalues are going to be 1 and minus 1, as you'd expect, the two nth roots of unity. Then the full eigenspace is going to be that little 2x2 Fourier transform, and then a tensor product with whatever basis you choose for the eigenvectors of an identity matrix. More generally, whenever you have a permutation, you can represent any permutation as a set of what are called cycles. So basically, you have like, maybe you have, let's say, this permutation. So we've got the numbers 1, 2, 3, 4, and 5. Our permutation swaps 1 and 2, and then it sends 4 to 5, 5 to 3, and 3 to 4. In this case, I have two cycles. I have this cycle of length 2 between 1 and 2, and this 3, 4, 5 cycle that's going between those three. So then this guy is going to have eigenvectors of plus or minus 1, the two second roots of unity. Its eigenvalues, plus or minus 1. Eigenvectors are going to be the 2x2 Fourier transform. Similarly, this guy, its eigenvalues are going to be third roots of unity, and its eigenvectors are going to be 3x3 Fourier transform. And then to get the eigendecomposition of this whole thing, just take a tensor product of those two pieces. So a tensor product of that 2x2, you'll be the eigenvectors, you'll be just sort of appending to each other. And then the I really wish I was going to go to the effort to edit this later, but I'm probably not going to edit this later. Sorry. Ignore that thing about tensor products. The thing you're going to do is append to the damn things. So if we have a block matrix here, this guy is going to look like this. This guy is going to look like, I think, this. Either that or the flipped version. So then the eigenvectors, you're going to have a couple 2x2 Fourier transform eigenvectors that are just 0 below that basically just interact with this part. Then you're going to have a couple of 3x3 Fourier 3x3 Fourier transform vectors that only interact with the lower part and are just 0 in the top part. And yeah, that's what your eigenvectors and eigenvalues will look like. So the point is, in general, when we have a permutation, we can sort of break it up into these cycles. Then we get eigenvectors and eigenvalues corresponding to each cycle, and then we reassemble them into one big matrix. That's how that works. Okay? Which means anytime that we have a system with this sort of symmetry in it, where we can do a permutation and then find that the matrix remains the same, we can get at least some information about its eigenvectors by looking at essentially Fourier transforms of parts of the matrix. In particular, Fourier transforms of parts that are symmetric. Which is sort of intuitively the reason why Fourier transforms are so useful. They show up in so many places. It's because, anywhere there's a symmetry, you can use a Fourier transform. One more thing to cover before we talk a little bit more about Fourier transforms. You can also apply this to systems that are sort of almost symmetric. So, for instance, in our ongoing example here, we have this 1 in each corner corresponding to the wraparound boundary conditions. But we could get rid of those wraparound boundary conditions. I could be like, look, man, I don't want my boundary conditions to wrap around. And then these two would both be 0. And the cool thing is, that's sort of it's still almost the same matrix in some sense, right? Well, in what sense is it almost the same matrix? It's almost the same matrix in the sense that it's the same matrix as before. Minus 2 is on the diagonal, it's below the diagonal, it's above the diagonal, 1 in each corner, plus this matrix which is just a 1 in each corner. And this matrix which just has a 1 in each corner, this is low rank. It's rank 2. It only has 2 non-zero elements, so it can't be more than rank 2. And I forget if it was last lecture or the one before that, but we talked about this idea that if you have a matrix that has some simple structure plus a low rank thing added to it, then you can always handle that using these relatively simple formulas for low rank updates, right? So if I'm trying to invert this matrix that no longer has wraparound boundary conditions, well, one way I can do that is I can invert the matrix with wraparound boundary conditions. For that, I can use my Fourier methods, because Fourier methods diagonalize this guy. That's great. This guy is nice and easy to work with. And then I apply a low rank correction to that. And that will be a very fast and efficient way of inverting this matrix. Okay. With that, all that covered, let's briefly talk about Fourier transforms. A little more. So you've probably heard before about the fast Fourier transform trick. I'm going to very briefly go over that idea. So the key idea behind fast Fourier transforms, first we'll write out the definition of a Fourier transform. So let's say Fourier transform of some sequence x, the kth element of the Fourier transform is equal to a sum on n, omega to the n, where omega is a root of unity. If we have, say, m elements, then it'll be the nth root of unity. And then x itself, that is big X, so I'll continue to write it as a big X. X sub n, so take the nth element of x, multiply it by the root of unity to the nth power, sum all those up, and that's basically your Fourier transform. Some variants will throw a constant in there somewhere. We'll just leave it at that for now. Now the key idea here is that we can separate this into two pieces. will sum over the even elements, so the elements of the form 2n, and then we have omega to the 2n x sub 2n, and then we can separately sum over the odd elements, sum over 2n plus 1, omega to the 2n plus 1, x sub 2n plus 1. And each of these sums is only going to be over half as many elements, obviously. Now, first sum here, this is equal to sum over half as many things of omega squared to the n. Now, if omega was an nth root of unity where m is even, then omega squared is also going to be a root of unity, but it's going to be a root of an m over 2th root of unity. Which means that this sequence is still going to be another Fourier transform, but it's a Fourier transform of half the size. So we're summing over half as many elements. We have our root of unity is like a half as manyth root of unity. So this is a 1/2 size Fourier transform. Then this other sum, the odd elements, we can pull an omega out of here, because there's this like plus 1 here, and then it's going to look exactly the same. It's going to be omega squared n x sub 2n plus 1. So again here, this is going to be a Fourier transform of half the size, except now it's multiplied by this extra omega. So this guy is, this is basically the decomposition that first became the famous fast Fourier transform. Whenever you have a Fourier transform on a number of elements that's a power of 2, so like you have like 64 elements, for instance, or 1024, or whatever it is, elements, you can recursively break it apart like this. You're going to have to break it down log n times in order to get it down to a trivial sized Fourier transform, and then you'll reconstruct all of those. It takes about n steps at each step to like add things up and multiply by these omegas here. So overall, the amount of work you're going to need to do here is n log n, whereas the Fourier transform itself, the raw matrix, is n squared. So you get n log n rather than n squared. That's nice. N log n is nearly linear, which means, remember, generally speaking, the cost of acquiring and storing data is roughly linear in the size of data. So as long as the number of operations you're doing is roughly linear, it's going to be plausible to actually do it. Whereas if the number of operations you're doing is superlinear, it will usually not be plausible to actually do it. So in this case, n log n, that's close enough to linear. It will usually be plausible to actually run Fourier transforms on large data sets. So that's the key idea behind fast Fourier. One little thing that I want to sort of emphasize to carry over to the next section is this operation where we're breaking it apart like this. We can write it as a matrix decomposition, and you do have to like sort of rearrange the x's to make it look nice. But the main takeaway here is that it ends up looking like this. You've got two sort of sub-Fourier transforms of half the size. So this is like this guy plus this guy. You apply those to x. And then you have diagonals like this. So you've got these four elements where like we're doing this multiplication by omega and then adding it over here. Sort of, yeah, this is the sparsity pattern that we get. And we're going to reuse a sparsity pattern which looks very similar to this when we talk about how to represent rotations in a minute. But right now I just want to emphasize like this is the sort of sparsity pattern that you get for a Fourier transform, assuming that you do a little rearrangement of the x's beforehand in order to group things together nicely. All right. That completes the section on symmetry and Fourier transforms. Now we're going to move on to the largely unrelated topic of how to represent rotations. So first of all, what's the use case here? Main place where this has come up in my life is when I'm doing some sort of optimization problem involving rotations. So for instance, maybe I have some matrix and I want to find a basis in which it looks kind of sparse, or in which the eigenvalues, or sorry, in which some measure of like the elements, the size of the elements of the matrix is minimized, any sort of weird thing like that. Point is, you have an optimization problem where you're optimizing over a rotation of some sort. Oh, another example would be I have two matrices, and I want to make them both sparse. Find a basis which makes them both sparse, or makes them both approximately diagonal. For instance, if I want to like approximately simultaneously diagonalize two matrices. Anyway, then I have a matrix that's a rotation, and I'm trying to optimize over it. Here's why this would be annoying to do straightforwardly. So like a first very straightforward thing that you might think to do is say, all right, a rotation matrix is just a matrix, you know, it's n by n. I'm just going to have this whole matrix, let's call it U. But now if I need U to be a rotation matrix, then I'm going to have some constraint on that. Namely, U transpose U has to be the identity. And, you know, optimization problems, once they have constraints in them, it's just like a lot more complexity to deal with. I would really prefer to not have explicit constraints. I would prefer a representation of my rotation that doesn't require explicit constraints in my problem. So how could I do that instead of this? First of all, a couple observations. How many degrees of freedom are in U? That's one thing we have to ask. So like, how many degrees of freedom will we need to have in our representation? So if U is like a bunch of columns, one way to think of it is our first column, the only constraint is that it has to have norm 1. So this is going to have, roughly speaking, n minus 1 degrees of freedom. One of our entries will need to be used to make sure that this vector has norm 1, but everything else can vary however they want. The second column has two constraints. It has to be norm 1, and it has to be orthogonal to the first column. So conceptually, we can use our first two entries to make it norm 1 and orthogonal to the first column, and then the rest of them are free to vary. And of course, there's like some fine details here. In fact, if these are like too big, then maybe we can't make it norm 1, but just the number of degrees of freedom here. And so on, like each time we add another column, that's one more constraint on the rest of the columns, since they all have to be orthogonal. So the total number of degrees of freedom here is going to be, number of degrees of freedom in that triangle. That'll be n times n minus 1 over 2 degrees of freedom. So whatever representation we end up settling on, it needs to have that many degrees of freedom in order to not have any constraints in it. A second consideration here, if we think about small changes in U, a nice identity pops out. If we just differentiate this equation right here, we get du transpose U plus U transpose du is equal to 0. We can rewrite this as U transpose du transpose plus U transpose du equals 0. So what this is saying, notice that this matrix is the transpose of that matrix. So what this is saying is that U transpose du is antisymmetric. That applies to any small change to U, which still leaves U as a rotation matrix, or an orthogonal matrix more generally. Now, this sort of suggests a format in which, like, there's a bunch of zeros on the diagonal, and then there's some stuff down here, and the negatives of that stuff up here. Like some sort of, like we want our differential element to be this antisymmetric matrix. So it'd be nice if we have some sort of like inherently antisymmetric representation for U. So those are like, and notice this has the right number of elements, because again, it's just like that lower triangle is your degrees of freedom. So this, it turns out that there is a representation which lets us do this. In particular, it looks like this. Take a matrix exponential of any antisymmetric matrix A. So it turns out that if you take an antisymmetric matrix A, you take its matrix exponential, that thing gives you an orthogonal matrix, or a rotation matrix in the relevant cases. And conversely, for any orthogonal matrix, you can find an antisymmetric matrix such that when you take the matrix exponential of that antisymmetric matrix, you get back the orthogonal matrix. So you can think about this in terms of an analogy to Euler's formula, like e to the I theta equals cosine theta plus I sine theta. So this is like the one-dimensional complex number version of this. Conceptually, antisymmetric matrices are sort of analogous to pure imaginary numbers. In particular, if you have an antisymmetric matrix, all of its eigenvalues are pure imaginary. And then, so in the one-dimensional complex case, this thing is what's behaving like a rotation, right? This cosine theta plus I sine theta sort of goes in a circle. And similarly here, each of your pure imaginary eigenvalues is going to be something that like goes in a circle. Right? So you can view this representation as matrix exponential of an antisymmetric matrix. You can view this as sort of a generalization of Euler's formula. So that's one way to represent it. That's pretty decent. The main downside is just that we have to compute a matrix exponential in our programs, which can get pretty complicated, right? Like matrix exponential is a reasonably complicated beast. So I'm going to suggest one other representation, which is a generalization of this form we saw for the Fourier transform. So looking at the Fourier transform format, we might think, hey, it'd be really nice if we could represent any of our rotations as like two rotations of half the size, and then these like four half-size diagonal operations. That's not going to work because there's not enough degrees of freedom in it. But we can add one more piece here. So what we do is we do two rotations of half the size, or two orthogonal operations of half the size, depending on the case. Then we do our four diagonal operations. Then we do another two rotations of half the size. And this, it turns out, does have the right number of degrees of freedom. And more generally, it basically works. There is a catch here. Not all of these are degrees of freedom. In fact, only one of these diagonals is an actual degree of freedom here. We'll talk about that in a moment. So the key idea here is if I take my orthogonal matrix or rotation matrix and break it up into four equally sized submatrices, then I have this formula saying U transpose has to be the identity matrix, right? That's my defining feature of an orthogonal matrix. Well, that means that U11 times U11 transpose plus U12 transpose has to be the little 2x2 identity. All right. Why is that interesting? Well, if I think about the eigendecomposition of U11 times U11 transpose, it needs to be the same as the eigendecomposition of this guy. Because if I just if I take identity minus, shift this around a bit, this is equal to identity minus U12 transpose. Whenever I take an identity plus or minus another matrix, that just directly adds or subtracts one from the eigenvalues without actually changing the eigenvectors. That's a general fact. You can check that pretty easily. I'm not going to go into that right now. So that means the eigenvalues of U11, U11 transpose, if we call those values lambda, they're going to correspond to 1 minus the eigenvalues of U12, U12 transpose. Furthermore, U11, U11 transpose, that thing's eigenvalues are going to be the singular values of U11. So these are going to be singular values, S squared of U11, meaning if I take a singular vector decomposition of U11, then first of all, the singular vectors I find will also be singular vectors of U12, and its singular values will be, or squares of its singular values will be 1 minus the squares of the singular values of U12. And those are going to be the elements on these diagonals. So when you take this idea, apply the same idea to U12 and U22, then to U22 and U21, then to U11 and U21, go through the whole shebang. What you'll find is that these diagonals have the form S, where S is the singular values, root 1 minus S squared, negative root 1 minus S squared, and S. So those are the diagonals. And then these guys, these sort of subrotations, are going to just be the singular vectors that pop out of each of these. So there will be 4 relevant sets of singular vectors. There will be this thing here will give us a set of left singular vectors, and there will be a set of right singular vectors if you swap which one's being transposed. And then there will be 2 sets of those when you actually go through all the relevant constraints here. The point is, main takeaway here, you take singular vector decompositions of submatrices of your rotation, and then you get this sort of nice recursive breakdown representation. And that has exactly the right number of degrees of freedom in it, and doesn't require complicated things like matrix exponentials, although it does obviously have a somewhat more complicated algebraic form than this. All right, that's it. That was all of the material planned for today. Thank you guys for watching.